In our previous sessions, we have started with the discussion of our interfaces, and we have also seen how to use your interface and what do you mean by an interface. And with one example, we have seen like how you're going to use your interface and what is your interface. And we also seen how to use your mod port and how actually the mod port is helping us to restrict the usage of signals by other modules, unintended modules, that and all we have seen in our previous lectures. So if you haven't watched those particular sessions, I recommend you to watch so that you can maintain the continuity of what we are going to discuss, right? Now, any doubts or any queries in this particular previous sessions? Shall we move forward with today's particular topic? That's great. Okay. Now, in this particular session, we are going to start with some new important topic, which is known as clocking block. Okay. So let us see what do you mean by this clocking block in detail. 1 minute, give me a minute. Let me activate this. So in this particular session, let us see about what do you mean by this clocking block. So this particular clocking block is mainly for synchronization purpose. Okay. So this clocking block, the syntax is basically clocking underscore CB, or it's basically clocking. The keyword we are going to use, which is known as clocking. Okay. Now, how to use this, where to use this? Let us try to understand with one example directly. Let's say if I'm going to have a module, this is my design. Okay. And you are going to develop a test bench across this particular design, right? Now, with respect to your test bench, you are driving the values. Basically, you are basically driving the values, and whatever the values your design is being sending, you are sampling them. That means you are collecting them. Am I right or wrong? So here we are doing two processes. One is driving the values, and another is sampling the values. Okay. Now, what happened to this? Okay. What happened? Give me a minute. 1 minute. Yeah. So with respect to your test bench, you are basically sending the values, or basically you are driving the values, right? And your design is responding to that particular values, and it is sending, or it is giving the outputs that you are basically sampling. Okay. So you are driving the values from your test bench and you are sampling the values to the test bench. So here we are performing basically two operations. One is driving. Okay, okay. I will share it one more time. 1 minute. So basically, we are driving the values. Here we are doing two operations. One is driving the values, and another is sampling the values. Okay. So driving means your test bench is basically providing the values to your design, and sampling means your test bench is basically collecting the values which your design is being sending. This is nothing but my sampling, and this is nothing but my driving. Okay. Now, can you tell me what happens if you are going to perform driving and sampling at the same time? What happens? Can we do that particular driving and sampling at the same time? Okay, what do you mean by race condition? Yeah, okay. What do you mean by race conditions? Toggling. Okay. What about this? What do you mean by race condition? One particular signal has been driven and sampled at the same time. Yeah, that is a condition I have said, right? So what happens if you are going to drive and sample at the same time? What is going to happen? Race condition. So what do you mean by race condition? What is the meaning of race condition is my question. Okay. So basically race condition in the sense, if you are driving and sampling at the same time, let's say suppose this is your this is your clock. At the same clock, you're trying to drive the value, and at the same time, you're trying to sample the value from the test bench. Then you might not get the proper output. Okay. Because you're basically providing some value to that particular design, and at the same time you're basically trying to get the output. Okay, so that is the reason you're not going to get the proper output. There may be some cases where you might not get the proper output. Okay, if you are going to drive and sample at the same clockage. Okay, so to avoid this particular race condition or this particular uncertainty, we are going to use something known as clocking block. Okay, so in this particular clocking block, how we are going to use this clocking block is using the syntax clocking. So within an interface only, I'm going to use a syntax which is known as clocking and followed by clocking block name. Let's say it is CB. Okay. And with respect to what this clocking block should work. Okay. Let's say with respect to positive edge of the clock, my clocking block should work. Okay. This is my reference clock which I'm going to take. Now, here I'm going to use something known as input skew and output skew. Let us try to understand what do you mean by input skew and what do you mean by output skew. So this is my clock. Let's say my design is working on the positive edges of the clock. Now with respect to this positive edges of the clock, input skew is nothing but this is nothing but my input skew. So this is nothing but my input skew and this is nothing but my output skew. So basically input skew is the time before the positive edge of the clock or active edge of the clock where your test bench is going to sample the signals. Okay, that is nothing but my input skew. Whereas my output skew is the time after the positive edge of the clock or after the active edge of the clock where my test bench is going to drive the signals. That is nothing but my output skew. Is it clear, guys? So basically input skew is nothing but the time before the active edge of the clock where testbench is going to sample the signals. That is nothing but my input skew. And output skew is nothing but the time after my positive edge of the clock where my testbench is going to drive the values. That is nothing but my output skew. Is it clear? So input skew, you need to strike that okay, it's the sampling time period, and output skew is nothing but it's the driving time period after the positive edge of the clock, whereas input skew is before the positive edge of the clock where the test bench is going to sample the values. Is it clear? Okay. If anyone having any query, please let me know. Yeah. Now let us see. Let us see how to use this. So I'm going to write down in the interface only clocking at the rate posage of clock is my reference clock which I'm going to take. Now let's say if I want to sample the values 1 nanosecond before my postage of the clock, then what I'm going to write down is a keyword which is known as default input hash 1. So before my 1 nanosecond before the clock, 1 nanosecond before the clock, I'm going to sample my values. Okay. And let's say I want to drive the values uh, at the passage of clock, at the passage of clock only. Then what I'm going to write down is output hash 0. That means I'm going to drive the values exactly at the positive edge of the clock, but I'm going to sample the values before the positive edge of the clock. That means here I'm going to sample. Without driving, you cannot sample it. So after driving your values, at this particular instance, you're going to drive the value, sample the values. That is, before this particular positive edge, you are going to sample your values. Okay. So this is how your input skew and output skew are going to work. Okay. Let's say, so if you mention this or if you don't mention this, these are the default values your clocking block is going to have. Let's say if you have another requirement, let's say default input hash 1 output 1.5 hash 1.5. Then what is going to happen? you're going to sample the values before 1 nanoseconds before the posterior of the clock, but 1.5 nanoseconds after the posterior of the clock, you're going to drive the values. Sampling is happening 1 nanosecond before the posterior of the clock, and driving is going to happen 1.5 nanoseconds after the posterior of the clock. So this is the meaning of this particular input skew and output skew. Is it clear for everyone? How I'm going to declare my input skews and output skews? Yes, no, clear, no, clear. Yes, yes. So let us see with this one example. When you're doing any simulations, are you going to face any setup and hold time, or are you going to consider any setup and hold time when you're working in Vivado, like or some model sim or synopsis tool, and when you're checking your what to say the simulations, have you ever checked for setup and hold times? Yeah, exactly. And if you want to consider the setup and hold times also, this is basically for inserting the delays only. Okay, if you're having considerations of your setup and hold time conditions, then for avoiding the violations also, you can insert this skews. This will help you to achieve your goals. Okay, yeah. So let us see one example with this. So I have a particular module which is known as multiplier. So this particular module So this particular module, I've written my input arguments. First, let us see the interface. So I've declared the interface and input is clock. So the interface can also have the arguments, okay, clock and reset. So this clock and reset will be given from the top module when we are creating the instance of our interface. Okay. And I've declared two variables A and B and one more variable out. Okay, and enable and ACK. Now, if I'm going to write down my clocking block CB, so here, what I'm going to do is I'm going to write down input 1.5, output 2.5. What do I mean by this? So sampling will be done 1.5 nanoseconds before the positive edge of the clock, and driving will be done 2.5 nanoseconds after the positive edge of the clock. Okay. So let us take it as one only, and input out and ACK. That means I'm going to sample the values out and ACK 1 nanosecond before the positive edge of the clock, but I'm going to drive the values A, B, and enable 2.5 nanoseconds after the clock. Okay, is it clear, guys? I hope it is clear, right? So this is how I'm going to mention my requirements which I'm going to have. Okay. Now, next what I'm going to do, I'm going to write down my mod port TB, and here I'm going to include my clocking block. Okay, so that I can able to restrict which particular module or which particular component can use my clocking block. No other components can use this clocking block until and unless we have given the access using the mod port. Okay, that's why I'm including them in the mod port. Clocking CB, input clock, reset. In the tasks and functions also we have seen, if you are going to include it in the mod port, then we can restrict the usage of that particular tasks and functions with to other modules and components, right? And another mod port for my RTL, where clock reset AB enable are my inputs and out and ACK are my outputs. Okay. And this is Testbench, and there is some particular code where I'm going to simply write down out is equal to A star B. This is the code and everything. Our major agenda is this particular clocking block. Our clocking block where from the test bench we are driving the values A, B, and enable. So this is my test bench. Let me show you. So this is my design, that is multiplier. Multiplier is not having any clocking block requirements. We are not going to have the clocking block for design. Okay. For the test bench only, we are going to use our clocking blocks. Okay. And this is my test bench. In the test bench, for driving my values A, B, and enable, I'm going to use the clocking block. That is, after 2.5 nanosecond, I'm going to drive the values. Okay. And before 1.1 nanosecond, I need to sample the values before the positive edge of the clock. That means this is my positive edge of the clocks. This is my clock. And here I'm going to drive the values. This is output skew is 2.5 and input skew sampling is basically 1.5. Okay. This let us try to check it out in our waveform, whether we are going to achieve it or not. Okay. So let me show you. Let me save this and relaunch it. We are not going to bother about the code and what is that which is present. Let us see whether we can able to achieve that particular behavior or not. Let me show you where I'm driving the values. Just that's I will show you. So here I'm driving the values tb underscore if. It's a macro which I've declared. This is a macro which is nothing but inf dot tb dot cb. That is inf is my interface name, followed by tb is my monitor name, and cb is clocking block name. So I've declared it as a macro. So dot a is equal to 5. That means this particular timing will be done. That means after the positive edge of the clock, 2.5 nanoseconds after a will be equal to 5, and 2.5 nanoseconds after b will be equal to 6. Let us check it out. Okay. So let me check out in this particular thing. Yeah. So this is my positive edge of the clock, and it is. Let me show you. This is my positive edge of the clock. Okay. This is 6 nanoseconds and 8 nanoseconds, 2 and plus zero point 0.5, 2.5. So 2.5 nanoseconds after my value has been driven to my design. Okay. And coming to this out also. Coming to my out, it is being sampled exactly at the positive edge of the clock. Because in the code we have written at the positive edge of clock, I am going to sample my values. In this is with respect to your design. So you are going to get your out at exactly the positive edge of the clock. I hope you are following me. Is it clear, guys? And what about others? Is it clear? Waiting for your responses. Yes, that's great. Okay. So more usage of this clocking block we will see when we are developing the test bench. It will be more interesting when we are going to develop multiple components in our test bench and having clocking blocks for each and every component. Clocking blocks for each and every component. That will be an interesting discussion to have. Okay. So because here in the test bench it is a planar test bench and we are going to have only one test bench model, right? So we cannot explore more things using this. And after learning like monitor, scoreboard, reference model, test bench. Sorry, only driver and monitor are going to have the clocking blocks. So we will see like two components if they are going to have the clocking blocks, like how they are going to react. Okay, that will be a good discussion, right? So this particular session, I wanted to just give you an intro about clocking blocks. So yeah, so that's about this particular session. And in next session, we will see about OOPS concepts. We will start with object-oriented programming. That will be a very, very interesting and very important part of our SV. Okay. Yes. So that's about this particular session. If you have any doubts or any queries you wanted to discuss, you can stay